на семинар просто приехать.
Молодец.
Да. Okay, I think that we can begin. Our today's guest is Eugene Ferapontov from Loughborough, and he will tell us about second-order integrable Lagrangians in WDVV equations. Eugene, you are welcome.
Thank you, Joseph. It's always a pleasure to attend this seminar and to speak. So I will speak about our joint recent work, relatively recent work, with Maxim Pavlov and Lin Xue from Ningbo University. So the title is Second-order integrable Lagrangians and Witten de Graaff-Verlinde equations. So this is, oops, second. So this is my plan. Can you see my slides? Is everything correct?
It's okay, yes.
Yeah. So I will start with first-order integrable Lagrangians, just to compare first-order and second-order Lagrangians. And the main topic are second-order integrable Lagrangians in 2D, in 2 dimensions, and in 3 dimensions. And okay, this is the I will derive integrability conditions in 2 dimensions. By the way, in 2 dimensions, first-order Lagrangians are trivial. In a sense, they're always integrable. But it's not the case for second-order Lagrangians. The integrability conditions are already non-trivial in 2 dimensions. So, and this link to WDVV equations, it's actually, it has been worked out in 2D, not in 3D. 3D is yet to be done. And then I discuss 3D Lagrangians, their relations to KP hierarchy, and in particular classification of Lagrangians with densities of this form. So it turns out that F is quite a non-trivial function in this case. And okay, my talk is based on this paper. All right, let me proceed to first-order Lagrangians. So I have one slide on first-order Lagrangians. These are Lagrangians of this form. So F is an arbitrary function of its arguments. U is a function of x, y, t, a function of 3 arguments. And Lagrangian density is a function of first-order derivatives only. So U itself and x, y, t.
I'm sorry, the function f depends only on these derivatives.
Yeah, only on this derivative. It doesn't depend on x and u, x, y, t and u itself, just on the derivatives. A familiar Lagrangian would be like this. If you suppose that f is the equation of the graph of a surface, then the area functional is square root of 1 plus ux squared plus uy squared plus ut squared, right? Area functional. So it would be a typical example. Unfortunately, this particular example is not integrable, right? But we looked, okay, the Euler-Lagrange equation corresponding to this Lagrangian is this second-order PDE. So it's written down here. This is the Euler-Lagrange equation. It's just a scalar second-order PDE for the function u of x, y, t. All right. Of course, it depends on f. We classified integrable Lagrangians of this form. We derived integrability conditions. This is integrability conditions is form a system of PDEs for this Lagrangian density F.
Zhenya, I'm sorry again, just a couple of words about the meaning of integrability.
Integrability is there are several equivalent approaches to integrability of such Lagrangians. First of all, you may ask that there is a dispersionless Lux pair, right? Dispersionless Lux pair in vector fields. All right, this is one definition. Another definition is integrability by hydrodynamic reductions. And another definition is integrability in terms of Einstein-Weyl geometry. Every second order PD generates a characteristic conformal structure, and we may require it as Einstein-Weyl in every solution. So all these three approaches are equivalent for systems of this form, and they give the same integrability conditions. But you see, I will say maybe a few words about second order Lagrangian. It was not my plan to stop on first order Lagrangians. Right? Maybe I can give a separate talk on this stuff. Right? Because these are old results. There are three equivalent approaches to integrability of equations of this type. The same approaches as they're integrable in the same sense as, say, DKP, dispersional SKP, or Bohr-Finley, or linearly degenerate PDs in 3D, in the same sense. All right. So what is important is that if you look at two-dimensional Lagrangians, so imagine that F doesn't depend on UT, only on UX and UY. Then this is your Euler-Lagrange equation. Again, it's a second order PD in two independent variables, and any such PD is linearizable. If you introduce UX, you call UX and UY by new variables, say A and B. UX is A, UY is B. Then for A and B, you'll get a 2x2 quasi-linear system, which is linearizable by a Hodograph transformation. So in 2 dimensions, every first order Lagrangian is automatically integrable, it's just linearizable. Right? But okay, my subject in this talk are second order Lagrangians. They will appear on the other slide. I'll just mention that there are these 3 papers devoted to first order Lagrangians, and this one is still, the last one is still in progress. All right, these are second order Lagrangians. They have this form. Lagrangian density this time depends on second order derivatives of some function. U of xy is a function, and only second order derivatives of this function are present in the Lagrangian density. All right. So it's a 2-dimensional system because we have only 2 independent variables, x and y. This is the Euler-Lagrange equation corresponding to this Lagrangian, and you see it's a 4th order PD, quasi-linear 4th order PD. And remarkably, its integrability, I will explain in what sense. The integrability of this PD is already non-trivial in 2 dimensions. And imposing integrability conditions, we get a constraint, we get a system of constraints for this Lagrangian density. All right. So in this talk, I will establish links of Lagrangians of this type to WDVV prepotentials of this form. I will explain what this means later. There will be a slide on WDVV equations. All right, so we have a prepotential of this form, and this function W is related by a contact-like, Legendre-like transformation to this F, Lagrangian density. So if you take integrable Lagrangian density and do certain transformation, Legendre-like transformation, then you get a WDVV prepotential of this kind. And okay, at the end, I will look at 3D second order Lagrangians. This time, U will be a function of xyt, of 3 independent variables. In this case, this is work in progress, and there is no direct link to WDVV yet, but there are interesting examples of Lagrangians of this kind. So, okay, let me show how to define integrability of Euler-Lagrange equations of this kind. Okay, here I copied the Euler-Lagrange equation, fourth order quasi-linear PDE for the function u of xy. Right, it's fourth order because this term in brackets, it depends on second order derivatives, and you differentiate it twice, so it will be a fourth order PDE. So first of all, I will introduce variables a, b, and c as follows, right? So uxx is a, uxy is b, and uyy is c, right? And then there are consistency conditions among them, like bx equals ay, cx equals by. It just follows from the definition. And then this equation, it takes the following form, f(a)xx, because f(u)xx becomes just fa. F is a function now of abc. F is a function of abc. So this fourth order equation takes this form. Now you see it consists of, it has three dependent variables, a, b, c. Two independent variables as before, x and y. And I have two first order equations for ABC, two first order equations, and one second order equation for ABC, second order equation. So, okay, I can make this system fully first order, four component first order system, a system of hydrodynamic type. So to do this, I introduce an extra variable, dependent variable P. It's a new dependent variable. And I introduce it using this second equation, last equation. So Py equals minus Fax, and Px equals Fbx plus Fc differentiated by y. If you cross-differentiate these two relations, you get this, right? So using this last equation, I can introduce P. Finally, I get the following system. My initial fourth order PDE for U, scalar PDE fourth order, is now a four component first order system. Ay is bx, by is cx, fcy is this, py equals this, right? Independent variables x and y, dependent variables are a, b, c, and p. And the system is clearly first order. So it's a hydrodynamic type system, right? Now, there is a theory of hydrodynamic integrability due to Tsarev. And it says that a conservative system is integrable. By the way, this system is conservative. Clearly, each equation is conservative. So this system is integrable if it's diagonalizable. So if we can find the Riemann invariants. And this can be efficiently verified by computing the Hantjes tensor, the so-called Hantjes tensor. So given a system of hydrodynamic type, you can efficiently verify its diagonalizability. I'm not writing here the Hantjes tensor. So there is a recipe how to do it, right? So you calculate a certain tensor. It's like when you check the flatness of a metric. You calculate the curvature, Riemann curvature tensor. When you calculate that to form defines a Poisson structure, okay, you essentially differentiate, you calculate this Schouten tensor, right? Schouten bracket. So same for hydrodynamic type systems, to check its diagonalizability, you calculate the Hantjes tensor, right? It's quite a complicated expression, but can be easily done by computer, right? So this has been done. And by the way, in this system, the unknown is one function, f of ABC, right? So for generic function, clearly this system will not be integrable, and integrability conditions impose constraints for this function of ABC. And these constraints, I will show you in the next slide. Right, so here is a system of integrability conditions, right? These are PDEs for the function, for the Lagrangian density. And my f of ABC is my Lagrangian density, right? And for this function of three variables, I have this system of PDEs. They come from the vanishing of the Hantjes tensor, right? So they're quite simple, relatively simple. They're all conservative. They're written in conservative form. Okay, and they're third order. Third order, they involve third order partial derivatives of this function f. All right. What we have done, we checked that, okay, this system itself is in an involution. So it's overdetermined, right? It's overdetermined, but it is an involution, right? It possesses a Lux pair. We can explicitly write Lux pair for this system. I'm not presenting it here in my talk, but it's available in the paper. And we can show, based on its involutivity, that the general solution of this system depends on 6 arbitrary functions of one variable. So this is the freedom in the existence of Lagrangian densities of this form. Remember that A, B, and C are UXX, UXY, and UYY, all right? So the freedom in such densities is 6 arbitrary functions of one variable. By the way, this will no longer be true when we move to 3D. In 3D, integrable Lagrangian densities form a finite parameter space. They only depend on arbitrary functions in 2 dimensions. What is quite remarkable is that this system is invariant under a very nice group, namely SP for R, symplectic group SP for R. And this group acts as follows, right? So let me introduce the matrix. So this system has ABC as its independent variables and F as its dependent, unique dependent variable. So ABC are independent variables, F is dependent variable. So first of all, I have to show you how ABC transform. So it's convenient to introduce this 2x2 symmetric matrix. Then this matrix transforms like this, where A, B, C, and D are constant 2x2 matrices, right? So each, this A, B, C, D are blocks, 2x2 blocks in this 4x4 matrix. So constant matrices, which such that this matrix, this 4x4 matrix, belongs to SP4R, all right? And by the way, this action is the standard action of SP4R on the 2x2 symmetric matrices. Or if such action is well known in the theory of Siegel modular forms, right? So the Siegel upper half space is precisely the space of symmetric matrices. Okay, strictly speaking, complex matrices, complex symmetric matrices with positive definite imaginary part, right? This is the Siegel upper half space. And the action of the symplectic group SP4R on the Siegel upper half space is precisely this. It's the analog of linear fractional action of SL2R on the upper half plane. Linear fractional AZ plus B divided by CZ plus D. So this has an analog for matrices, for symmetric matrices, right? So this is how my independent variables transform, ABC, and the function F, dependent variable, it transforms like this, right? It transforms like this. So this transformation law is quite remarkable, because if you saw the transformation law of Siegel modular forms, then F transforms precisely as a Siegel modular form of weight -1. In general, what are Siegel modular forms of weight K? It's the following thing. It's a function defined on dependent on ABC, depending on ABC, on a symmetric matrix, which transforms precisely in this way, where instead of this determinant Cu plus D to the power -1, you have determinant Cu plus D to the power K, right? And these are called Siegel modular forms of weight K. So this suggests, this transformation law suggests that our object should be somehow related to Siegel modular forms, right? Unfortunately, we do not have a precise construction that justifies this. I will show you some solutions to this equation in theta functions, in elliptic functions. but still we don't have genuine modular forms in the final answer, right? Furthermore, so the symmetry group of this system, it consists of these transformations, which form SP4R group, and also this transformation. What this transformation does, it just adds to F a trivial Lagrangian, right? So remember that F is a Lagrangian density. Okay, nothing changes if you multiply Lagrangian density by a scalar coefficient, non-zero scalar, right? If you add a constant, or if you add a linear combination of uxx, uxy, and uyy, nothing changes in the Euler-Lagrange equations. So these terms just disappear from the Euler-Lagrange equations. But if you add this Monge-Ampere thing, uxx uyy minus uxy squared, right, to the Lagrangian density, it's also a trivial Lagrangian, right? Monge-Ampere term is a trivial Lagrangian. So its Euler-Lagrange equation is identically zero, it's trivial. So in other words, adding to the Lagrangian density F all this tail doesn't change Euler-Lagrange equations. So this is our symmetry group of the system. Okay, it's finite dimensional, but it suggests a link to Siegel modular forms, right? Okay, probably now I will say a few words about WDVV equations. So what I will show next is that this system of integrability conditions for the Lagrangian density is related to the so-called WDVV equations, Witten, de Graaf, Verlinde equations. So I will, in the next two slides, I will briefly remind you WDVV equations. Right, so, okay. In general, what are WDVV equations? Now for a second, we forget about integrable Lagrangians. So we have a function f of n independent variables, right? F of u1 and so on, un. It's called prepotential, just a function of n variables. With the following, with two constraints. First of all, you form this third order partial derivatives. You see this first variable is u1, and then ui, uj, where ij can take all possible values from 1 to n. So I can take any value from 1 to n. So 1 is also allowed. But the first variable is fixed, it's u1, so it's a marked variable. So first condition, that this matrix is non-degenerate and constant, right? That's the first constraint on the function f. This matrix is constant and non-degenerate. So here u1 is a marked variable. I will call it eta ij, so we can invert it. So for instance, we can form eta is with upper indices, which is the inverse of this. It's non-degenerate, so we can invert it. All right, let's then introduce the following object, Cijk. You just calculate third order partial derivatives of our function, this time with respect to all possible variables. So u1 is not present here necessarily, right? u1 is also part of these variables, but they can be any variables from 1 to n. And you raise the one index, this index s, with respect to eta is, right? And this gives you the coefficient Cijk. And then we require, okay, these Cijk's are functions. They all depend on this u's. They're not constants. They depend on u's. Eta is a constant matrix, but Cijk's are functions. And they're expressed in terms of third order derivatives of this function. And we require that they satisfy the associativity conditions, right? Clearly, associativity conditions, so we require that the algebra with this structure constants is associative. It's clearly commutative, right? It's commutative because partial derivatives j and k commute. So it's a commutative algebra by definition, and we also require it's associative. Clearly, these conditions, associativity conditions, they give a complicated system of PDEs, third order PDEs for the function f, right? For the function f. Another object I will need are the so-called primary flows, commuting primary flows. These are hydrodynamic type systems generated by this potential, right? So the main object is this potential. It satisfies certain PD system, and it generates n commuting hydrodynamic type systems of the following form. So UIs are now becoming functions of variables T alpha times and x. UIs are functions of T alpha and x. And the equations are like this. So UI differentiated by time T alpha is eta is F US U alpha. F is this prepotential, right? All differentiated by x. So what is written here, for every fixed alpha, for every fixed T alpha, I have a hydrodynamic type system, right? If I take T1, then this will be a trivial flow. So in fact, there are n-1 commuting flows of this kind. T alpha times of these flows. So these flows by construction, they are Hamiltonian, and the Hamiltonian operator is this, and the Hamiltonian density is this, right? So these are primary flows. So I will not need the general case of this construction. I will only need a special case when the number of U's, the number of variables equals 4, right? And the matrix eta is a 4x4 anti-diagonal matrix with ones on the anti-diagonal. So 4x4 anti-diagonal matrix. This corresponds to the prepotential of this explicit form. So what I will need is this particular prepotential, right? So you see its dependence on U1 is special. Its dependence on U1 is special. If you calculate this matrix, U1, UI, Uj, you will see, okay, when you differentiate by U1, this W disappears. And from here, you will see that all these components, eta, ij, are constants. So this will be a constant matrix, and associativity conditions impose a system of differential equations for this W, which I will show you on the next slide. Right? Associativity equations are PDEs for this function W. I will say a few words what will happen next, right? So I claim that associativity equations, these equations for W, will be equivalent to conditions on the Lagrangian density, right? And second, remember that I reduced the Euler-Lagrange equation for Lagrangian density to a four-component system. So four-component system will be one of these primary flows corresponding to this prepotential. So this is the precise relation, right? This is the precise relation. Everything can be written down explicitly. So I will write an explicit formula which takes a Lagrangian density and constructs this function W. Right, it's given by explicit formula, right? Okay, let me continue with WDVV equations. Now I will write down the associativity condition. So I will call, to comply with my previous notation, I will introduce U1, U2, U3, U4. Remember, these are the arguments of F, right? I will call them now P, B, C, and A, right? Then my prepotential takes this form. And the associativity conditions, because A, B, C, and P were the variables for the Lagrangian density. So it's convenient to use this notation. And the associativity conditions are reduced to the system for W, which is shown here, right? This is a third order, oops, sorry. This is a third order nonlinear PDE system for W, for prepotential, right? And I claim that this system is related to the integrability conditions for Lagrangian densities for this system for F, which was discussed above. And the link is a sort of a composition of a Legendre type transformation and the potential substitution. So it's not precisely a contact transformation. It involves potential substitution followed by a partial Legendre transformation, by contact transformation. Okay, so let me go back to associativity equation, to Lagrangian densities. Here, now I want to construct an explicit link between Lagrangian densities f of ABC, and WDVV prepotentials. Let me remind you that this system, four-component system, appeared before when I derived integrability for Lagrangian densities. I wrote Euler-Lagrange equation in four-component form. This is it. I just copied it, right? Okay. The first thing I want to write this system, four-component system, is in Hamiltonian form. Remember, I required this system to be diagonalizable, and I obtained integrability conditions for it. Okay, so now the next remark is this system is Hamiltonian. To see this, we apply partial Legendre transform. We change from f of ABC to h of capital A, B, and C, where this Legendre transform is here. It's a contact transformation, classical contact transformation, called partial Legendre transform. In fact, it's Legendre transform in the C variable. You see, A and B variables, they stay the same, but C variable transforms as in the partial Legendre transform, all right? So this is a partial Legendre transform. If you apply this transform, then this system takes this form, which I call number one. Then I get this, right? It's equivalent system. Now we can see that this system is Hamiltonian. This is its Hamiltonian density, and this is its Hamiltonian operator, right? Anti-diagonal matrix. And finally, the last comment, this was observed by Maxime, that if you set in this system H equals WC, you introduce a potential transformation, right? H is WC. Then this system becomes one of the primary flaws of this prepotential. Remember, each prepotential has primary flaws, and one of them will be precisely this system, right? So now, in fact, I will show you the explicit link between W and F, which appears here, Lagrangian density F, and this prepotential W of ABC, and it's written here. You see, it's a composition of a Legendre transformation with a potential substitution, because this is, you see, this one is a Legendre transformation, and this one is a potential substitution. The composition gives me this, shown here in red. So let's say I've shown quite a few changes of variables and formulas, but what is important to remember is this, the only thing that is important to remember. So if we have a Lagrangian density, f of ABC, of small a, b, and c, then we can reconstruct this prepotential W of capital ABC by these formulas. And vice versa. If we have a prepotential W of capital A, B, and C, I can reconstruct Lagrangian density f of small ABC. It's more or less one-to-one, right? All these relations are consistent, and so why is it useful? Because from some Lagrangian densities that we found, we can construct in principle potentially new prepotentials, WDVV prepotentials. And other way around, there are many explicitly known WDVV prepotentials. Lots of them are known explicitly. Polynomial expressions, expressions in rational functions, expressions in theta functions. So you can take any of them and you can reconstruct using these formulas the Lagrangian density, integrable Lagrangian density. So this is the link. I will later use these red formulas to do some computations, but okay, you just believe me that there is this formula. It establishes a one-to-one correspondence, more or less one-to-one, between integrable Lagrangian densities and WDVV prepotentials. But my goal is to say something about Lagrangian densities, to show you some examples. Okay, let me show you some examples. So partial classification results. You see, it's not possible to describe all Lagrangian densities. Remember, I stated one of the statements was that they depend on 6 arbitrary functions of one variable. So Lagrangian densities are governed by an integrable system. I can't solve it explicitly. Like I can't solve explicitly KdV or Kp, right? Same here. I can't solve this system explicitly, but I can construct many solutions, right? For instance, this is a very simple polynomial second order Lagrangian density. So F is Lagrangian density. Now I'm returning back to the notation Uxx, Uxy, Uyy, which I called ABC, right? I call them ABC. Okay. So this is a cubic polynomial in ABC. And this particular Lagrangian appeared in the paper by, I think, Mironov and Bialy on integrable geodesic flows on a 2 torus, right? They reduced the equations of this integrable geodesic flows to the Euler-Lagrange equation of this system somehow. Right? There is another very simple example which governs Newtonian equations with 5th order polynomial integrals. So this equation is governed by Lagrangian density, which is 4th degree polynomial in Uxx, right? Okay, it's again second order Lagrangian integrable. Both are polynomial integrable Lagrangians. Then we found quite a non-trivial example. We looked for a Lagrangian density in this form, e to the Uxx times some function of the remaining 2 variables, Uxy and Uyy. And we obtained a PDE system for this function g, right? And it turned out that this function g of BC is expressed in terms of the Jacobi theta function. And here delta is the modular discriminant, doesn't matter. It's quite a tricky formula. And remarkably, if you construct a prepotential, WDVV prepotential corresponding to this Lagrangian density, we will get a known WDVV solution, which corresponds to averaged NLS equations. But when we did this computation ourselves, we didn't know this link. It was kind of found independently, right? Then there are Lagrangian densities in terms of dilogarithms. For instance, F is alpha is a constant times some function of Uxy plus this elementary function. Okay, if you substitute this into integrability conditions, you get for Q, you get a certain ODE, which is straightforward to solve, and Q is determined in terms of dilogarithm. Q is this formula where dilogarithm is this, this quadrature, right? Okay, and there are many other examples. I will not show you other examples. I will show you a few examples coming from WDVV prepotentials. I'll show you one example. I will take known WDVV prepotentials. Many of them are explicitly calculated. I will construct the corresponding density. Lagrangian densities from polynomial prepotentials. There is a classification of prepotentials with nice symmetry associated with Coxeter groups. With any such prepotential, I can associate my Lagrangian density. In general, it will be an algebraic function in ABC. In some cases, it will be a polynomial function. So, okay, let's take this particular prepotential. Right? It was calculated by Dubrovin with collaborators, probably Bertola, probably Stron, and maybe I'm not sure. They had another collaborator, D. Young. I'm not sure 100%. I forgot who was another contributor to this. So here the function W is this part, and this part, the first two terms, is the part depending on T1, right? So this is a polynomial prepotential, and if you plug this into the equations, remember red equations connecting Lagrangian densities with prepotentials, you get this F, Lagrangian density, this thing to the power 3/2. There is another very similar prepotential. In fact, it just, you can swap T2 and T3 in this equation, in this relay equation. It turns out that, okay, T2, swapping T2 and T3 is a simple, obvious symmetry of WDVV, but it gives quite non-trivial, makes non-trivial effect on the corresponding Lagrangian density. Because our change of variables is not symmetric on the interchange T2 and T3. Our link, sorry. So in this case, we get this polynomial prepotential, right? So this F gives this polynomial, gives this polynomial Lagrangian density, right? And there are lots of other examples that we calculated. I'm not showing them here. So you take various known solutions of WDVV and you calculate a new Lagrangian densities, integrable Lagrangian densities. Right. Now 3D case. I have 4 more slides. Is it all right? I'll just quickly go through 4D.
Yes, Jenny,
I have 4 more slides. And then, so I'll say a few words about.
We are in no hurry at all. So
okay, good. But our results here are more sketchy in 4 dimensions, right? For instance, so now we are looking at these Lagrangians. U is this time a function of x, y, t of 3 variables. And the Euler-Lagrange equation will be a 4th order PD for U, right? Remarkably, this problem again has the same symmetry as before. So where you take for capital U is the Hessian matrix of my function U, Hessian matrix, and it transforms like this. Hessian matrix transforms like this, and F transforms like this, right? So this is modular symmetry. It suggests a link to Ziegel modular forms, which has to be still elaborated, right? It's work in progress. Also, we can add to F a trivial Lagrangian. What is a trivial Lagrangian? You take the Hessian matrix U of the function little u, 3 by 3 Hessian matrix, and you consider a linear combination of all possible minors of this matrix, like all these Monge-Ampere terms. This sum is called a trivial Lagrangian. Here, lambdas are arbitrary constants. These are trivial Lagrangians. They generate empty Euler-Lagrange equations. So clearly, we can add to our Lagrangian density F a trivial Lagrangian. Nothing changes, right? So this is our symmetry. And quite remarkably, right, in the 2-dimensional case, this symmetry in some sense was not enough. It's finite dimensional symmetry. But the solution space for Lagrangian densities was infinite dimensional. You know, they depend on 6 arbitrary functions of 1 variable. But here in 3D, the class of Lagrangian densities of this form, integrable densities, is far more narrow. And they in fact form a finite parameter space, right? And so there is a hope to more or less classify all of them in some sense, right? Because this group becomes more or less sufficient. It acts transitively on the solution space. So it's completely different story. All right, but okay, I'm not presenting you equations, conditions of integrability, because we don't have a nice form for them, like in the 2D case. We can't write them in a very simple form. There are lots of them. They live in the computer. We can calculate with them, but we can't write them in a nice form yet. Okay, let me show you some examples. Lagrangian densities, so we have only examples in 3D. Lagrangian densities coming from KP hierarchy. Look at these formulas. I show you 3 Lagrangian densities. At this stage, at the beginning, ignore all red terms, all terms shown in red. Just look at this expression. It's a second order integrable Lagrangian density. And if you add these corrections, it becomes Lagrangian density for one of the commuting flows in the KP hierarchy, right? So it's no longer kind of quasi-linear. If you cross out these red terms, you get a dispersionless, a flow of the dispersionless KP. If you add the red terms, it's the full dispersive KP. And you see this sum is finite. You don't need anything else. So this Lagrangian, dispersionless, black Lagrangian, it possesses this dispersive extension, which contains only finitely many terms, right? And okay, the rest examples are similar. They have a similar structure. It's some dispersionless bit, this bit raised to the power 3/2, plus this dispersive thing. And again, this Lagrangian describes one of the commuting negative flows of KP hierarchy. And same for this. It's just a different negative flow, right? So these examples show that it is an interesting problem to, if you have a Lagrangian, this second order Lagrangian, to find its dispersive extension. Does it always exist? It's entirely open. In these particular cases, okay, it does exist, but in general, we don't have such statement. And let me show you quite a sophisticated example, very funny example of a Lagrangian density in 3D, for which we do not know dispersive extension at the moment, right? And it's strangely related to the Lobachevsky function. So let me show you the formulas. So let's look at Lagrangians of this form, which only depend on mixed derivatives, uxy, uxt, and uyt, nothing else, right? Just this. So uxx, uyy, utt are not present. All right, so you can calculate integrability conditions for Lagrangians of this form. You get a relatively simple system of PDEs for this function f, which we managed to solve completely, right? It was not so straightforward, it took us quite some time. Now I want to explain how to solve this system. How to solve this system. First of all, let us introduce variables. Uxy I call v3, uxt I call v2, and uyt I call v1, right? So the arguments of this function are v1, v2, v3, all right? Sorry, other way around. v3, v2, v1, right? Doesn't matter. So these are the arguments of this function. Okay, then let me introduce variables a, b, and c by these formulas. Quite sophisticated, tricky formulas. You have trigonometric functions on the right and hyperbolic functions on the left. But you see, we know v1, v2, v3. So via these formulas, we now know a, b, and c. All right? Small a, b, and c. Now let's do the following. Introduce a spherical triangle. Triangle that lives formed by geodesics on the unit sphere. Spherical triangle. It has sides A, B, C, and it has opposite angles, capital A, capital B, and capital C. Just usual side lengths, usual angles, right? But it's a spherical triangle, so its sides are arcs of great circles. They're geodesics on the sphere. So I have this spherical triangle with side lengths A, B, and C, and angles A, B, and capital A, B, and C. Then we have the so-called cosine, spherical cosine laws. These are the relations which hold for every spherical triangle, right? They hold for every spherical triangle. right? Remember that these variables, small a, small b, and small c, we already know. We express them in terms of v1, v2, and v3, right? So now we can use these formulas to express capital A, capital B, and capital C. In other words, with this v1, v2, v3 variables, we associate a certain spherical triangle with side lengths ABC and angles capital A, capital B, and capital C, which are explicitly expressed in terms of v1, v2, v3. Right, this is what I need. Then the claim is this function f of v1, v2, v3 can be obtained by this quadrature. Can be obtained by this quadrature, right? It satisfies this relation. Its differential is capital A are the angles, capital A, capital B, and capital C are the angles, and A, B, and C are side lengths. So this df is this function, right? And it's, by the way, it's not so obvious that this expression on the right-hand side is a total derivative, right? It's not immediately obvious, but this kind of formulas, they are known in geometry, especially in hyperbolic geometry. It turns out that this function f, it somehow has the meaning of the volume of a certain tetrahedron, hyperbolic tetrahedron. But okay, let me first show you the final answer for the function f, right? What is the formula? This thing needs to be integrated, and it's not so straightforward, although this is a closed form. I think it took us about a month to, or maybe even more, to find an a primitive for this one closed form. The right-hand side is a closed form. So I'll show you the answer. So this function f is given explicitly by this formula. It's the sum of these, it's irrelevant, minus these, minus these, right? Remember that capital A, capital B, and capital C are the angles of the corresponding spherical triangle. So they're explicitly expressed in terms of v1, v2, v3, right? And this L is the so-called Lobachevsky function. It's this integral, special integral. It's not an elementary function. It appears in the theory of hyperbolic volumes. So you see the integrable Lagrangian density of this form is a highly sophisticated object, somehow related to hyperbolic geometry, right? Somehow related to hyperbolic geometry, and the reason for this is not yet clear. There must be some deeper relation why this is all related to hyperbolic geometry, right? Something to be understood. So, and the work, there is a work in progress on kind of characterizing integrable Lagrangian densities in 3D in terms of Ziegel modulo forms. So it's the same authors, including now this time Sasha Desky. And this is my last slide, and thank you very much.
Oh, Zhenya, thanks a lot.
Mm-hmm.
Well, quite impressive.
Mm-hmm.
The last part. So, question. Okay, that's it. Thanks a lot. So we meet as usual next Wednesday, the same time, and everyone is welcome. And Zhenya, thanks a lot again. And
thank you very much. Thank you for having me.
See you in Moscow.
All right, see you.
Goodbye.
Bye.